Hi, good afternoon, and welcome to this seminar talk. Today we have a great speaker. I'm really pleased to introduce Professor Haiping Lu from University of Sheffield. So Professor Lu is a professor of machine learning and AI strategy at the Department of Computer Science and the senior research director for healthcare data and AI in the University of Sheffield. His research interest focuses on developing translational AI technologies for better analyzing multimodal data in healthcare and beyond, particularly multidimensional data and heterogeneous graphs in bioinformatics and medical imaging. So welcome you all, and welcome Professor Lu. Over to you.
Thank you, Lee, for the invitation, and thank you all for coming. So today I'm going to talk about learning from healthcare data across domains and modalities. By the way, for those online, can you see me and hear me clearly? Good? Okay, great. So firstly, a brief introduction of my group in Sheffield. We call ourselves PyKale, right? So PyKale stands for Knowledge Aware Machine Learning. In one line, our objective is to learn from multiple data sources for better prediction and understanding. So I have started to work on machine learning since my PhD from 2004. Actually, I started working on machine learning from 2005. I started focusing on dimension reduction, basically tensor factorization model, and then later on moved to sparse models. And then I also worked on neural networks, mainly convolutional networks and graph neural networks. And more recently, we started focusing on knowledge-aware machine learning, where we work on multimodal learning and also transfer learning. And then we built a machine learning library called PyKale, which is part of the PyKale ecosystem. So in terms of applications, we focus on two primary areas. One is image analysis, in which I started to work on brain imaging, which is brain MRI, and then we move on to work on cardiac imaging, which is MRI for the heart. And then gradually move to the other big area I've been growing in Sheffield, which is drug analysis. We started working on drug discovery, try to predict whether drug will find with target. And we work on knowledge graph, right? We use knowledge graph to model data and do prediction. And we also work on multiomics, how to integrate different kinds of multiomics data for prediction. And we also develop our Haiping library so that we can put all things under one umbrella. So today I'm going to talk about all of them except cardiac. So we talk about the imaging across domains and modalities, and drug discovery across domains and modalities, and knowledge graph and multiomics across modalities. So let's start with our work on brain imaging across domains and modalities. So this work will be talking about our recent paper on improving multi-site autism classification through site dependence minimization and second order functional connectivity. So here is a 2D embedding of the brain functional connectivity, the network feature of 1,035 patients or subjects from 20 sites. That's these are sites, some from New York, some from Stanford. You can see NYU. That's Stanford. From here, you can see, right? So there's a problem for machine learning, for example, right? So if you train your data on NYU data, right? So you may not be able to do well on Stanford data, right? Because the data distribution are different, right? Although the same human brain is for MRI, but the features are different, right? The distribution are different from one side the other side, and there are 20 sides, right? And 20 sides. Even from the same machine inside, right? It close, but still like right? So these features you can see is size specific. And what machine learning prefer is this, right? Because machine learning we learn from prediction, learn from distribution, and we want to make predictions, right? So therefore, machine learning prefer the data to look like this, right? If you randomly pick samples, it should represent the whole population, right? So therefore, that's what machine learning prefers. So how, right? How can we go from here to there, right? How can we go from that size specific feature space to this more like homogeneous feature space, right? What we do is to do domain adaptation. So we use this, we commit the maximum independence domain adaptation to adapt the feature space from size specific to something more evenly distributed across the feature domain. Right? That's what we do. So basically, for the whole pipeline, we take the brain network feature, right? That's the brain atlas. And then we compute the network features over here. That's just 3 different ways of computing features. And then we do domain adaptation so that the feature view goes from size specific to something more homogeneous and evenly distributed, right? So that we can learn and do this. And in this work, we also take into consideration of additional data modality, which is phenotypical information, for example, the set of the subjects, and their candidates, whether left handed, right handed, age, and scan and IQ. And then we use typical, like traditional part of application. So here are some results we show in the paper, which I want to highlight 2 aspects. One is adaptation works, right? If you compare this approach, this is raw, that means the first figure is 2, right? So that kind of size of the figure, that's the performance. And this is after the domain adaptation, right? So we can see if we compare orange versus orange, blue versus blue. Right? So that's the first observation, is that domain adaptation can help to improve the prediction. The second observation is that feature matters, right? So what feature you use, it matters, right? If you use different feature, you get different conclusions. For example, here the best result is obtained when you consider the phenotypical information. Right? So you see that by considering the phenotypical information, you can improve the prediction law. Right? So let's look at the left explain. Yeah, the first one is traditional, like PyKale cross validation, where you do random split, right? So therefore the data mix. Second one is more challenging, where we put the one side out. That is, we use 19 sides for training and the 20 sides for testing, right? So that is more challenging, but also more close to real world scenario. For example, we think that all the data in all of UT and then maybe use it in somewhere in US or in Germany or in France, right? So that is, we call it the one side out prediction. You can see the prediction is much, it's more challenging than when you're doing random split, right? So this will be more realistic, and they basically examine the domain outside of domain prediction performance, right? So that's why the one side out of domain prediction is more challenging than in domain prediction. Second, domain adaptation can improve the performance. Third, feature matters. Whether you use just correlation, like just correlation, or use another kind of more advanced correlation for testing, then we also have a second order feature, right? So it just matters if you work on this feature, you can over the conclusion. You do that they are actually getting worse. Right? So therefore, it's important to have the right feature, and that's why we want to look at the results have see what kind of data we have to leverage back one by one. So those are the three key observations from this work. And then let's move on to the interpretation part and the understanding part. Right? So by adopting using those classical classifiers, which are mostly linear, for example, we make linear SVM, and these are also linear, and we can do interpretation by identifying which features are important at higher rates. That's more like traditional statistical analysis, and we can highlight to the domain experts in that by doing the prediction, maximizing the prediction accuracy, we found those features contribute the most to the prediction. And so then this can help us to understand how the classifier works, how the prediction is doing, and then we can do follow-up studies based on that. So this is our biomarker visualization to highlight the brain connectivity features that contributing the most to accurate prediction. And let's move on to another work on graph analysis, which is drug discovery. So this is the recent work published actually last Thursday in Nature Intelligence. This work aims to predict the drug target interaction. So we have a drug and we have a target with a protein. We want to predict how much they will bind with each other. So whether they will bind it so that it can have an effect, or whether it will not bind. Right? So basically, it can be a binary prediction problem. So what we developed here is a network that will learn the substructure of the drug and the protein, the target. Here, what we do is we use graph and multiple network to learn the representation of the substructure of the drug, which is actually the atoms. Right? So basically, each of this lecture is a representation of the atom in that drug. And so this is one atom, this is the next atom. Each row is an atom. So this becomes a matrix, right? The matrix will become the feature representation for that drug. And for the protein, for the target, we model it as a 1D sequence. Then we also learn the features for the substructure. Every here, for example, every 3 letters will be learn a feature. So each row corresponds to 3 letters. And then after we learn for the whole sequence, we also have a matrix that is protein representation. That is drug representation. And then what we will do is that we will explicitly model the interaction between the substructure, right? Between the drug binds with the target, they should happen on the substructure level. So we want to explicitly model the interaction between the substructure, and for example, this row can be the drug representation, that is protein representation, and this will model the interaction between a particular atom with particular subsequence of the protein. And we also use multi-head attention, which basically is to say that we assume that there are multiple relationships, right? So therefore, we learn multiple these matrices, right? Not just one. Using one matrix, you can capture one kind of relationship, right? And then we use multi-head, multiple matrices, then we can learn multiple kinds of relationships. And then after we learn this kind of relationship interaction, this is what we call bilinear interaction maps. Then we can do a bilinear pooling, basically extract features from those multi-head attention and have a joint representation which capture the interaction between drug and protein. And then we will feed this into a fully connected neural network to do the prediction. We can predict the probability of how likely we are going to interact with each other. And furthermore, we also apply a domain adaptation method to help to improve the out domain performance throughout the next slide. So here are some results. Firstly, I will show you from left to right different way of evaluation. Right? So on the left most is random flip, right? So that's more like a textbook way of evaluation. Let's say, okay, you have data set, try to do random flip, right? So randomly flip your data set into training and test, and then do the performance evaluation. It turns out this usually is the most optimistic way of evaluation. Usually it gives you very good results. Just imagine you have all the data, random mix and random samples. It can give you really very good results, right? But that's not what happens in the real world. Right? When we collaborate with academics in the beginning, so that guys will tell me random result, right? We do something, but it doesn't work. That's not how the real world works, right? So then there's what we call tone split, right? The tone split is basically you make sure that the drug and target in the screening set do not appear in the test set. So in other words, you are testing on drug and the target that you have never seen, right? So you didn't see at all. That's called tone split, right? So that's much more challenging. Right? So you see in the test set, the drug and target has never appeared in the training set, right? So and also their interaction, so on. So you can see that's much more challenging. And therefore, different way of evaluation can give you different conclusions, right? So indeed, one of our papers shows, right? If you use differently, you can get all the conclusion, right? One paper says, okay, A is better than B, but if you change the evaluation, then B is better than A, right? So, and there are also, even if you do code split, there are still kind of information leakage because some of the drug or protein although you didn't see, but they may come from the same family as a training set. Right? So therefore, that's still not challenging. What's most challenging is what we did is clustering based probability. Right? So therefore, when we have the data, we try to cluster them into different groups. You can make another table with the multi-site or the classification, right? Basically, each site is more like a cluster, right? So therefore, we will cluster the drug and targets so that different clusters will be very different. And so then we do clustering based propagation. So we use all except one cluster at training and then test on the remaining cluster. That's much more challenging than those states. Right? So therefore you can see the accuracy also becomes lower, right? So this is basically more like cross-domain evaluation, and for random space, that is really in-domain evaluation. And so that gives you an idea of how things can change, right? So the concurrent testing, and basically we started the performance on 3 data sets with MongoDB, FastMap, that's the number of drugs with in the data set, that's the number of proteins. And that's the number of interactions in the data. So this is the largest data set with 49,000 interactions. And we also studied the adaptation, whether it can help to improve the baseline, which we showed that indeed, right? So if we do the adaptation, we can further improve the results. So this is about the prediction performance. And how about interpretation and understanding, right? So one of the lessons of working in healthcare is it teach me very early on, don't think only about prediction numbers, right? So you really have to think about the interpretation, explain the things to people and help people to understand. Therefore, when we design the network, we take things into consideration, and our design helps us to have molecular level insights and the interpretation, right? So therefore, by training our model, we can interpret how the drug actually interacts with the protein. And so here is some illustration. This is the 2D structure of the ligand with the drug, where by training the model, we can tell that which atoms are contributing the most to the binding, right? Those are basically in the, if you remember the 2D map, those are the atoms corresponding to large weights. So we can tell, okay, these atoms contributing the most to binding. And we can also examine the ligand protein interaction map, right? That just shows how what are the important substructures from the protein that are interacting with the ligand, and whether this kind of interaction, for example, is consistent to what is already known in the data. So, and we also further show the ligand protein binding pockets in 3D space. So this is the drug, this is the substructure, how they interact, and this is the drug, right? This is the drug. And that is the protein 3D map, and that is how we get the 3D structure. You can tell that you have the protein data bank where you can have the same 3D structure, right? So we can examine and see what are the correctly predicted amino acid residues and what are the corresponding ligands. And of course, you can read our paper, right? It's not all perfect, right? So we also have incorrect prediction. Right? We have explanation of why, because we model the protein structure as 1D sequence, right? But protein actually is 3D structure, right? So therefore, we use further simplified structure. So therefore, we cannot fully capture the really information, but we do have some findings that are consistent with what is already known. So that is our second work on drug target interaction prediction. And the third work is on knowledge graph, and here we are trying to use knowledge graph. We integrate data from multiple modalities. So basically, we use knowledge graph as a way of doing data integration. So this work is called GRAPH, which is called Graph Information Propagation Network on supergraphs. So here we consider multiple data sources. For example, it can be a conventional database with organization, location, food, and business. And what we do here is we consider the relationship between different types of entities. And for example, here we will consider the organization and location as similar type of entities, and we group them as what we call super vertex, and focus is super vertex, and the business will be a super vertex. And here is that we want to capture the semantic relationship between different kinds of entities, different kinds of data. Therefore, when we have this super vertex, we can simplify our modeling process. We can determine the super edge, that is how the information flows, right? So here, our target is the book, right? Here, what we want to predict, what we want to know about is the book, right? So therefore, the information flows from the organization location to the book and beginning to the book, right? Here, we want to do prediction on books, right? Book is our target. So we can determine the super edges and determine how the information flows. And then we can learn the node embedding for these super vertices based on the everything. Right? So we learn the node embedding for the location and the organization, and learn the node embedding for the book and also for the business. And then after that, we learn their representation. Remember the 2D matrix, right? For the atoms and for the protein here similar, right? So after we learn the representation, then we have a decoder trying to decode for prediction problem. For example, we can classify the node classes, or we can predict the link types, right? So what kind of relationship they have, or what type of node they give, right? So whether they is fiction book or it's a romance or whatever, right? So this is the overall flow of how we do the learning So that is, for example, the original data. You have locations, organization, you have book, and you have business. And then, as I said, we model it using super businesses. So we view it as one type of data, as one type of super project, and then we model their relationship here, our target book. After that, this defines how we want the information to go from one way to the other. Then for different supervisions, we start from a raw representation. And then we use graph convolutional networks to aggregate the information within their supervision. And we try to aggregate the information from different nodes, right? Because the books they are connected to each other, right? So you try to collect the information from the neighbors, and then we have an updated representation. After that, we do a internal aggregation, right? So we do another level of aggregation, and then because this one is the target, so we integrate the information from the business and the location organization together to another network. It's basically aggregating. We really check the information, right? Get some information from there, try to aggregate, making a new vector, then pass on. The next level, you aggregate the information again. Then after that, you pass the information, propagate the information to your target and to another level of learning and aggregation. And then you have the final representation. Then the final representation as a vector can use it for prediction, classification of a node class, or predict the relationship between two groups. Right? So that is how the data flows, right? How we use super vertices and super edges to learn the models from different data sources, right? From different data sources. And we have applied this to drug-drug interaction prediction. Here is we apply to a polypharmacy side effect prediction. That is when you take multiple medicines. Now these people may have multiple drugs, and you take multiple drugs, you may have side effects. So here, the task is really to predict if you take drug A and B, what kind of side effects are you going to have? So here we do the study on 19 nodes, that is 19 genes or drugs, and the 6 million edges and basically 1,000 plus edge. That means 1,000 plus different side effects. And so here is our BigNet performance. Basically, what we show here is that our network is much faster to train. As you can see, because this is one of the key constraints is the computer power we have. So you can see we can reach up to high accuracy in a short time. And secondly, is the embedding dimension, because every vector, the dimension of the vector is determining how much memory, for example, RAM, you need in order to do it completely. So we also show that our model performs very well in the low dimension. Here, only 8. That means each of the nodes, each book is represented by 8 numbers, and it can perform well over existing network. So that is our server called BigNet, which is not graph to model the different kinds of data sources. The last technical work we are going to talk about is multiomics, where we develop a multimodal point feature selection methodology, where the problem of multiomics is that you have different omics in genomics. There are genomics, epigenomics, and so on. And so on. There are many more. But here, what we are doing is to model the different omics as a graph themselves. And then we build the connections by construct the wave graph by considering their correlation. and relevance from the networks, so that we can maximize the relevance and also minimize redundancy between the different features. Right? So here, what we are doing is to review all the always data features together, and we want to do the feature selection by considering all of them all together, right? Their relationships. So here, what we study is a GTJ, where we use it for cancer diagnosis, and we consider 3 different kinds of omics with about hundreds of samples. That's about on the scale of 300, that's 20,000 features. And here we do a simple comparison. Our methodology is basically unsupervised method. That is, we do not look at the label when we do joint feature selection, and we compare with the supervised method. And we can show that we can perform better than the supervised method with having information of the label. So those are the technical work papers that we have recently published on learning from healthcare data across domains and modalities. The last piece of work, which is something of my big passion and also is really my baby, is PyKale and PyKale. PyKale is our my first effort actually is to build the library. And so this is really thanks to COVID. Right? Because when the COVID, I cannot go back to China with my parents. I thought I have so much time left. Right? What should I do? I will have a baby. Right? This is my PyKale. So PyKale is built for knowledge-aware machine learning from multiple sources in Python. So we our paper has been here published in CIGM last year. That is a repo website. And our library has also been officially become part of the PyKale ecosystem. Right? So this is really a good example of being high, because when we just started, I have no idea about building a library, but I think this is really true. Right? So I just told my team, okay, if we work hard on building this library, then one day we will become part of the PyKale ecosystem. Right? And that time I couldn't believe it, right, myself. But after 1 year of our working, it didn't come true. Indeed, we become part of the PyKale ecosystem. That's information from Facebook, which has Meta, and recently PyKale was donated to the open source foundation, the same as Linux, become fully open source. So we have very good news here. So why I want to build such a library is because when in Sheffield, when we do research being interdisciplinary every year, there's an issue, and the issue is that basically you can see there are machine learning is thriving, and there are lots of powerful tools out there, PyTorch, scikit-learn, SciPy, Multi-modal, SLPy, so many tools out there, but the people who have access it is limited, and particularly for domain experts, right? So they may not have the skills to make use of those tools. Therefore, what we do is we find a machine learning expert or data science who can help them to make use of tools to do their research. Right? So that is how they, for example, my collaborators approach me to help us to analyze our data, solving our problem. So, but after you define a few times, you have to say no, because people have limited bandwidth. Then in the beginning, I say yes, but gradually I have to say no, I don't have no bandwidth. Therefore, for these who cannot find a machine learning expert to help them, basically they do not have access to such powerful tools out of it. They do have access. So that is a major issue, and that inspire us to develop PyKale. Another reason is that there are dedicated libraries for particular modalities, for example, for text. There are LTK for images, imaging data, there are collinear and so on. For graph data, there are PyKale. But if you want to use all kind of data in one project, it's really difficult. Because you know how to use this, use that, and that. Basically, raise the value higher. So therefore, it's very difficult to manage a project involving multiple data modalities. So therefore, if you have a project, you want to deal with multiple modality, that is more challenging. Right? And therefore, it also makes it more difficult to use those powerful tools. Therefore, we think that instead of helping the new expert directly, we want to build something that can help them interact. So that is, we want to build a library that will be more accessible to all the domain experts. Instead of helping them directly, we want to build a library that will be more accessible by domain experts. Okay? So then we will build the interface to access the powerful machine learning libraries out there. So when we try to do this, also benefiting from my years of lecturing, because we teach hundreds every year, 200 students from various backgrounds. I realized also we look at different codes. Right? If you look at the same thing, same machine learning pipeline, you can see the code. Some of the codes, they will have a full module, right? This is my machine learning module, right? From head to right? in one class, whatever. And you will see also some always 4 steps and 9 steps. And you will see also some programs and many steps. Right? But these are all doing the same thing, but it looks very different. The problem is standardization. Right? The things are not standardized. And even the same thing looks very different. So it builds a lot of barriers. Right? We build a lot of barriers and confusion. And we invent a build or waste of efforts. So what we want to do is to build a pipeline-based API that we can standardize the process. Right? So therefore, based on my experience, we have standardized the steps of machine learning pipelines into 6 steps. Right? First, we know the data. Second, we process the data. Third, the embedding that is learning feature. Third, to the prediction. After that, we do the evaluation, and then do the interpretation. Right? So that is the 6 steps. And what I do, personally, I start with everything. I start with figures. So that from figures, we can standardize into 6 steps. Level entry, standardizing figures, learn, in feature, predict classes, complete accuracy, realize the pattern. And for medical imaging, for MRI, for brain MRI, for cardiac MRI, we follow the same 6 steps. Learn the data, standardizing, learn the features, predict the classes, from the accuracy realize the pattern. And also for drug discovery, we do follow the same 6 steps. And learn the data, learn the technical character, that's a MET, as you can see the protein sequence. Learn the sequence feature, do the embedding, the prediction, evaluation, and realize the relationship. Right? So I standardize all the machine learning pipeline in the same step. Right? So therefore, the first level API all looks the same. And even more, we also standardize all the examples and the code configuration. Right? So we basically separate the code. We separate the code and the configuration. And what we do is we want all our examples look almost the same, right? Almost the same. Therefore, when you get familiar with one example, and when you move on to the example, you see almost exactly the same file. Configuration file, link file, tutorial file, configuration. It looks all the same. Right? This can greatly reduce the barrier. Already for medical imaging, for drug discovery, or for M&A stage application, right? It looks all the same. I think it can help you greatly reduce the barriers. Right, so that is a very brief introduction to PyKale, our effort. So we think there are 3 key benefits for machine learning experts like us. One is that it can help us to reproducible reason, right? For example, those kind of configuration files are very important, right? So if you have worked with machine learning, you can see some of the lines they have multi-lines, like 5 or 6 lines of parameters, right? So sometimes really, really difficult to define, right? So therefore, you have a configuration file, you put all the configuration into one YAML file and save it whenever you get a result, have to produce more reproducible. Secondly, it's scalable collaboration, right? So that is one of the motivations of why we develop PyKale is because I can only help a small number of researchers, but through this library, we can help more, right? So that we can have more scalable collaboration. And build this library, makes it more accessible so that more researchers can use it. Then basically, that's the fact that we are helping more and we're collaborating with more research. That's what we call scalable collaboration. And also, by standardizing the API and put different kinds of data like imaging data, graph data, text data, speech data, all under the same set of API under one same umbrella, it makes it easier to develop cross-boundary models, right? So they are all under standard API. I think, oh, this model or this feature embedding feature pattern or prediction that have been very successful in text, I can apply to images. This method that is very successful for images, I may apply for graphs. This method, this API, this particular class, which has been shown to be very successful to graph, I can use it for text or speech. Right? So that makes it much easier to develop cross-boundary models. And for end users, we provide off-the-shelf machine learning pipelines. We have very specially configuration editing, which we don't have to learn Python. We learn simple descriptive YAML configuration. You can configure machine learning model and run it. And we also support multiple modality under one roof. And most important, we are open with very strong community engagement. We have a lot of community engagement features, discussion boards, forums, whatever that's very standard in the whole community. So that is an introduction to our research in machine learning across domains and modalities. I have introduced to you how we learn from imaging data across domains and modalities. In, for example, incorporating phenotypic data and query and get much better results. From discovery across domains, when we find a model, it by class makes the space so that we can have more related modeling. And knowledge graph by using knowledge graph to integrate data and multiomics where we deploy feature selection. And of course, these work are not possible with our hardworking team members, collaborators, and these are our academic collaborators. And this is my MSc student, my NSC and PhD and PhD. And this is my NSC student, who is now at UPSC. It's my new PhD student, right? And the open source library has reviewed from a lot of other researchers as well. Last but not least, finally, Sheffield, we have a new our own AI center. We thank Martin for organizing this nice seminar series for the Computer Science and AI Institute, Manchester. Finally, after much later, we will have our new center for machine intelligence. Right? So I myself will be recruiting 5 AI research engineers built on top of Haiping to build standardized pipelines to help researchers outside our own domain, outside skill. People in research science, in art and humanities, and we will have the advertising ready soon. And we will recruit our director for Center for Machine Intelligence to have advertising come out very soon. And we also currently have opening machine learning, robotics, computer vision. The deadline is 22nd, 8, and the 6th of March. All right. the best way of engaging or get connected is to follow LinkedIn, get connected on Twitter, and also check the website are opening. And thank you very much.